representing electrons as dots is a drastic oversimplification, right? Because we just learned more than we wanted to know about electrons and the wave-particle duality and all of that crazy stuff. And now we're just going to make them be dots on a piece of paper? Well, it makes it a lot easier to think about. But this is a very, very drastic oversimplification. So we have so far been talking about electrons being shared and have kind of assumed that the electrons are shared equally, but that is not always the case. When the electrons are not shared equally, this is called a polar covalent bond. So here we have a representation of hydrogen fluoride. So we have the hydrogen atom and a fluorine atom, and this is showing us the electron density. And so there's more electron density around the nitrogen and less around the hydrogen. This is like when you went on a trip with your family and had to sleep with your sibling in a double bed, right? And they were always taking the blanket during the night, right? The blanket should be shared equally between two people sleeping in a bed, right? But it never is. There's always one person who hogs the blanket, right? So here, fluorine is the blanket hog. Fluorine is hogging the electrons. They're spending more time with fluorine. And as a result, the fluorine end of this molecule becomes a little bit negative. And the hydrogen end becomes a little bit positive because the electrons are not being shared equally. They're spending more time with fluorine. So here we have, we've got this lowercase Greek delta plus and delta minus to indicate which end is a little bit positive and which end is a little bit negative. And they're floating around between these two plates and metal plates, and they're just, randomly oriented in space. If we charge these plates, so this one's negative and this one is positive, those little molecules are all going to spin around and line up like compass points. And the positive end will go and be pointing towards the negative plate, and the negative end is attracted to the positive plate, and they're just going to all line up in that electric field. Well, how do we know which element is going to hog the electrons? That's called electronegativity. The ability of an atom to attract electrons to itself in a chemical bond. This is inversely related to atomic size, and this is a three-dimensional representation of the periodic table showing relative electronegativity. Electronegativity is on a 4-point scale, kind of like grades are. So 4 is the highest and 0 is the lowest. Fluorine is the most electronegative element. So there is a relationship with atomic size, but it's not just atomic size. So the way I remember this is fluorine is the top dog, the best blanket stealer of all of them. Electron hog, supreme. As you get closer to fluorine, whether you're going across the periodic table or going up, they're going to become more electronegative, more attractive to the electrons. The electrons will go towards them more in a bond. Now, there's actually another column on the periodic table that's not shown here, the noble gases. We don't consider electronegativity with noble gases because they form almost no compounds. So there's no point in talking about electronegativity with them. So we just leave them off this. So there may be homework or worksheet questions where you actually have to look at these values. So fluorine is a 4.0, and these other guys are smaller. You will not have to do that on an exam, okay? So you don't memorize this. The thing you need to memorize here is fluorine is the king, and as you get closer to him, they're more electronegative. I guess she would be the queen, whatever. So this is the kind of question that could show up on an exam. Arrange these elements in order of decreasing electronegativity. Phosphorus, sodium, nitrogen, and aluminum. And we're going to do this just based on trends in the periodic table, not by actually looking up their values. The values are useful sometimes, but what's more useful is just being able to identify between two different elements which one is more electronegative. So we have to find these on the periodic table first. So here's phosphorus, and sodium is over here, and then nitrogen's up here, and aluminum. Let's try that again. So we're going for decreasing electronegativity. That means we want the most electronegative one first. This is how it shows up in a multiple choice exam. I recommend not looking at that. Put these in order yourself and then find this one, the one that matches. Because that can just, like, those letters start to swim after a while, and then you forget what you were even doing. So decreasing electronegativity. Let's find the one that's most electronegative. Who is closest to fluorine? Nitrogen. Nitrogen is closest to fluorine. So nitrogen is the biggest. Oops, that's not at all what I meant to do. Nitrogen is the biggest. And so that's that one. Who's next closest to fluorine? P, phosphorus. So phosphorus has a lower electronegativity. And next farthest away is aluminum. And then farthest away is sodium. So then we look over here and find the one that matches, and it's letter A. Okay. So things like predicting trends in lattice energies, not super important, just not. Being able to identify which element is more electronegative in a pair is actually pretty important. And that's important all the way in and through OChem. So this is something you really do want to pay attention to. So bond polarity. Oops, wrong button. So here we have an illustration of a pure, I don't use that word much, a non-polar covalent bond. Here's where the electrons are shared equally. And so we see this, kind of looks like a peanut. It's very symmetrical. This would happen if you had two identical elements, right? Like if the yellow is fluorine, this is a fluorine and another fluorine, they are exactly the same. One isn't stronger than the other, one isn't more electronegative, so they're going to share the electrons equally. At the other extreme is an ionic bond, where here, it's not that the electrons are shared unequally, it's gone so far that one of them lost an electron to the other one. And in the middle, we have a polar covalent bond. The electrons are shared, but it's not equal. Where do we get to the... trying to figure out where my analogy belongs. I'll just do it right here. So we can indicate using these deltas that this is negative and this is positive. Another way to indicate the polarity of a bond is by using an arrow. So the arrow points to the more electronegative one, and we put a little plus on the other end. So this kind of ties into the metallic electron C model, where the electrons are little boys playing in the neighborhood. So we can think about these bonds as being two little boys playing with each other. One came from this house and one came from this house. And they're going to play together. They're going to stick together, and because this is shared, they're going to be between the two houses. But how do they decide whose house to play at? Well, what if this house has all the satellite channels and all the game systems, and they actually have a soda fountain in the kitchen with like 5 different sodas you can have? And if you say you're hungry, the mom will order pizza. Cool. They got a pool in the backyard with a diving board and a slide. You got trampoline, everything you can imagine. Over here, not so much. Small black and white TV with an old VCR and a few old Thomas the Tank Engine videos. Right? If you're thirsty, you can get a glass of water, and you might get some crackers if you're really hungry. No game systems, no pool, just not as fun to play, right? So the electrons are more attracted to this electronegative element. So they're attracted to it just like little boys would be attracted to that really fun house to play in. Would they never go over here? Well, this guy might need to change his underwear once in a while. He's probably sleeping over at this guy's house most nights because it's just more fun. But they're still shared, they're still going between, okay? Over here, the houses are the same, and so they're going to spend more equal time. And this is like the extreme situation where one family actually adopts the other family's child. All analogies get a little strange when you go too far, right? So what's the division between a nonpolar covalent and a polar covalent bond? Well, there's a continuum right here. We were looking at the electronegativity difference, delta En, En for electronegativity, because that's kind of a long word to write out all the time. So obviously a difference of 0 means those two elements are the same, and it'll be perfectly shared equally. But then there's all these different possibilities. So the difference can be anywhere from 0 up to 3.3. 3.3 is the largest difference because there aren't any elements that have 0 that are worth talking about. So we've drawn some lines, and they are somewhat arbitrary, right? It's like, you talk to people, was your family rich growing up, or were you poor? Well, how do you define that, right? It's relative, right? Someone who's poor in the United States probably seems incredibly wealthy to someone in a third world country, right? So it's all relative. There's, kind of arbitrary distinctions that we make. So these are the distinctions. If the difference is 0.4 or less, we're going to say that's close enough to 0 to call that nonpolar. If we get a difference of 2 or more, we're going to call that an ionic bond, completely transferred, which we'll find out in a minute doesn't actually happen. And then in here, shared unequally. Okay. These divisions here you might need on a homework problem or a worksheet problem. I won't ask you to remember those for an exam. Okay? They measure bond polarity using something called a dipole moment. It's like a senior moment or something, I'm not sure, but a dipole moment with the symbol mu. That occurs whenever there's a separation of positive and negative charge. So the dipole moment, and we're not going to do anything with this equation, the dipole moment is equal to the charge magnitude and r, the distance between them. So common unit is the debye, which is equal to this many coulomb meters. It's in the book, I've said it, we don't care about that. And then here we're going with small electronegativity difference, intermediate, or large. We can also talk about percent ionic character, because as it turns out, no bond is 100% ionic. So there, I've said it. We're going to pretend that they are, because for general chem, it's just easier. But what we really mean by an ionic bond is that if it has over 50% ionic character. So this is a graph of percent ionic character versus electronegativity difference. And so what we see down here in the less than 25% category, these are nonmetals with each other, right? Nonmetals form covalent bonds with each other. Above 50% ionic character would be considered an ionic bond, and all of these are metal-nonmetal combinations. This guy's pretty close, hydrogen fluoride, really close, but still under 50%. Two nonmetals, covalent bond. So, we should be able to look at two elements forming a bond and identify them as polar covalent, nonpolar covalent, or ionic. And we don't have to consider any of those numbers. Most of this is stuff we already know. These simplified rules will not cover everything, because there are pairs of nonmetals that are different elements, but they have identical electronegativities, and so they will form a nonpolar covalent bond. But for everything that we need to know this for, that doesn't matter, okay? So this is what I expect you to do on an exam, answering questions like this. So here we're supposed to identify if these are nonpolar covalent, polar covalent, or ionic. So a bond between iodine and iodine. Pardon me? Pure covalent, yep, or nonpolar covalent. So this is nonpolar. They're the same, right? The two houses are the same. The electrons are going to be shared equally. Cesium and bromine. Ionic. And you really do have to take a peek at the periodic table, because where's cesium? He's way over there. Cesium is a metal. Bromine's over here, non-metal. They're different, but the metal-non-metal means it's ionic. How about phosphorus and oxygen? That one's going to be polar covalent. It's two nonmetals, it's a covalent bond. But they are different metals. Back up. Two nonmetals, it's a covalent bond. But they're two different elements. And so we can assume that their electronegativities are different. Okay? Any questions? Yeah.
What kind of bond was carbon and hydrogen again?
Carbon and hydrogen is a nonpolar covalent bond. So these are both nonpolar, and if you have different elements, it's polar. Any question?